For modern pyroprocessing systems, the clinker cooler offers the greatest development potential for further reducing specific heat consumption. For the past 10 to 15 years, air beam technologies have capitalized on this development potential. However, this capitalization has not been without added complexity in terms of air piping, dampers, and sealing air fans. Recognizing that these side effects may have an impact on the cooler's overall availability, F.L. Smith and Fuller set out to develop a cooler that was less complicated, more efficient, and easier to maintain than any other cooler on the market. The result of this intensive development effort is the Smith-Fuller Crossbar Cooler. Simplicity is the hallmark of the new cooler. Operation of this cooler and maintenance of this cooler are so simple that increased availability of the kiln system is a natural development. The SF cooler is fundamentally different compared to any other clinker cooler in that the two primary functions of the cooler have been separated: conveying the clinker and cooling the clinker. The grate line performs no conveying function. It is completely stationary. There are no moving grates. Rather, a simple series of reciprocating crossbars located above the grate line are used to convey the clinker. These crossbars are separated from the grate line components by a protective layer of stationary clinker. By separating the conveying mechanism from the cooling mechanism, cooling efficiency no longer deteriorates over time, and the sealing air fans that are required for air beam coolers are completely avoided. The crossbars effectively convey, mix, and shear the clinker layer. This has the dual effect of conveying the clinker while at the same time preparing it for its efficient exposure to cooling air. Beneath the crossbars is a grate line with individual air distribution plates that are locked together to prevent the possibility for clinker fall-through. With these air distribution plates, an innovative cooling process has been introduced which is amazingly simple, while at the same time remarkably efficient. On the bottom of each individual cooling plate is a rectangular tower. The tower assembly of each cooling plate contains a weighted regulator. The regulator consists of a special valve which hangs from the tower. The hanging valve acts as a variable orifice that moves relative to the difference in pressure on either side of the valve. Because the pressure immediately below the air distribution plate is a measure of the resistance of the material layer above it, the regulator opens to compensate for an increase in the measured resistance, or closes to compensate for a decrease in the measured resistance. The regulators are specially designed to maintain a constant airflow through the cooling plate and into the clinker layer, irrespective of process conditions such as bed height, particle size distribution, temperature, and so on. In this way, every grate plate in the cooler is continuously provided with the quantity of cooling air that it needs. The regulator maintains a specific airflow rate throughout its entire range of movement. By carefully selecting the weight and flow pattern of the individual valve that hangs from each of the towers, a constant flow rate is attained. The efficiency of the cooler can, therefore, be optimized by installing different flow regulators at different positions within the grate area of the cooler. The regulator, thus, controls the amount of cooling air that flows from the undergrate chamber into each individual grate plate. It is like having an individual cooling fan for every grate plate in the cooler. The use of the mechanical flow regulator greatly simplifies the operation of the cooler. There are no pipes, dampers, or sophisticated electrical controls for the operator to be concerned with. The mechanical flow regulators ensure optimum air distribution during all operational occurrences. As a result, the thermal efficiency of the SF cooler has been demonstrated to be superior to any other type of clinker cooler, including the most efficient of air beam coolers. The air distribution plates are protected from heat and wear in two important ways. First, the plates do not move, so they are not subject to moving wear. Second, there will always be an insulating layer of clinker located between the active bed of clinker and the air distribution plates themselves. The grate line is completely stationary so that the use of side castings and side seals are completely avoided. The grate plates themselves are no longer considered wear parts, and no refractory ever needs to be disturbed to replace a grate plate. The sealing system for the grate line is so effective that no devices are provided for removal of spillage from the undergrate chamber. The bottom of the undergrate chamber has a steel floor without any openings. No spillage removal valves are provided, and no spillage conveyor is required. This means less items for maintenance. The fixed grate line for the entire cooler makes it possible to construct the entire cooler out of several pre-engineered, pre-assembled modules. In fact, the entire SF cooler is constructed as a modular system, with one controlled impact system, followed by several standard modules. Individual modules are 4 cooling plates wide and 14 cooling plates long. The modular design allows for different configuration patterns depending upon the production level and clinker temperature requirements. Individual modules are simply set side by side and end to end. The standard modules are pre-assembled in the workshop to ensure high quality, swift and easy installation. In fact, entire coolers will be stocked as off-the-shelf items. For retrofit applications, complete demolition of the existing cooler and startup of the new cooler can typically take place in as little as 25 days. Each module consists of a movable frame activated by a hydraulic cylinder. The movable frame is connected to a pair of drive plates which reciprocate the moving crossbars. The movable frame is much simpler in both design and construction than a conventional movable frame. It does not support the grate plates or the grate plate supports. It supports only the drive plates to which the movable crossbars are attached. The drive plate penetrates the grate line via 2 slots which extend throughout the entire module length. On top of the drive plates, a patented sealing profile forms a dust trap, preventing clinker from entering the undergrate compartment. Since the grate plates do not move, it is possible to make a very effective seal between the fixed grates and the moving drive plate. The sealing profiles extend throughout the entire cooler length, which means that during the reciprocating movement of the crossbars, the ends of the drive plates are never exposed to wear by the clinker. Each module has 7 stationary crossbars and 7 movable crossbars, which reciprocate in a manner similar to grate plates in a conventional cooler. The crossbars are attached to the drive plate by a retainer bracket that attaches to ears extending from the drive plate. The retainer bracket and crossbars are locked by wedges driven in by hammer. Replacement of the crossbar is simply made by knocking the wedges out with a hammer and removing the retainer bracket. The number of wear parts has been minimized through simple design. These wear components are designed to last 1 campaign or more. All wear parts in the cooler are easily replaced, typically in less than 2 days. Cooling air is supplied to the undergrate chamber of each module by fans equipped with piezometers. The mechanical flow regulators are so effective that the required number of fans is only determined by the number of modules set end to end. That is, modules set side by side have their undergrate chambers joined so that only one fan supplies air to both the right and left. In this way, a 4,000 ton per day cooler, for example, will only have a total of 6 cooling fans, one for each of the 5 modules in length, plus 1 fan for the controlled impact module. In conclusion, the SF cooler is significantly more simple to operate than an air beam cooler. The use of mechanical flow regulators is like having a separate cooling fan with its own flow control for every grate plate in the cooler. As a result, there are inherently less items for the operator to control. Manual dampers and internal piping associated with air beam systems are completely avoided. Moreover, the separate sealing air fans required by such systems are no longer required. The mechanical flow regulators are self-regulating, so sophisticated controls are not required, and inherently fewer fans are needed. In addition, the SF cooler is significantly more simple to maintain than a traditional cooler. By separating the conveying and cooling mechanisms, it is possible to employ a fixed grate line for the entire cooler. Simple replacement of all wear components yields less downtime for your kiln system. In summary, there is good reason to believe that the crossbar cooler will define the way that clinker coolers are installed, operated, and maintained in the future.